All right, let's just go ahead and get started. This week, we're going to be looking at adversarial search, search with an enemy. In all seriousness, right, when you think about a two-player perfect information board game, which is what we're going to be looking at, a zero sum, as it's called, by which we mean one person's got to win, one person's got to lose. You know, I might sit down and play chess with a good friend of mine, but for the duration of that game, we're enemies, right? Only one can prevail. Or you might tie, but where's the fun in that? This particular problem, developing an AI to play a board game, has been a fixation of the field of artificial intelligence since its inception. The earliest AI checkers player goes back to the 1950s. It was actually, and so like all the main ideas that I'm going to go over today were all invented by this one guy in the 50s. And obviously there have been lots of improvements since then and refinements, but the essential ideas were developed by a guy named Arthur Samuel, and he was doing checkers. And this is about the 1950s, and he worked for IBM, which at the time was one of the few computer companies that existed. And what he would do is, at that time, the computers were mainly running and in operation during regular working hours. He kind of pioneered the idea of programming is done largely at night. That is, when the computers were not heavily in use, he would go in at weird hours and run his checkers programs and try to get the AIs working. So we're not going to go over everything he did, but the main ideas we're looking at in outline are all essentially the ideas he came up with, which remain influential to this day. And many of these ideas are at the heart of what modern chess programs and the like all do. So one little oddity I should mention is that in recent years, checkers in particular has transitioned in status to that of a completely solved game. That is, what people have done is pre-computed a database containing 444 billion different chessboard configurations, both openings and endgames. And it turns out, using the techniques we're going to go over today, the search algorithms are able to connect to the two. And so perfect chess playing engines actually existed. Checkers players engines existed. Chess, not so much. But for checkers, they exist. Another popular game for which there's perfect engines is Connect 4. And Dr. Yorgi has a book on Connect 4. He's just fond of the game as a pastime. And he was showing me that there are certain sections where it's talking about what's the best move in this situation. And the book will just say, you know, the best move is absolutely this, because they analyzed it in a flawless Connect 4 engine. So, but these same concepts underlie chess engines that we're going to look at. In previous years, I actually had chess as the assignment for this unit, but what I learned was we don't really have enough time to actually do a particularly good chess program. So people worked on it, and then their chess programs just weren't that great. But with checkers, using the ideas we're going to discuss, you should be able to come up with a pretty intimidating opponent by doing this stuff. Not necessarily flawless, but definitely intimidating. So, without further ado then, let's go over how you think about this. So, this is thinking of the AI for this task as a search problem with a search tree, very much as what we examined in the case of this maze and the 8 puzzle, and so forth, which is to say, you've got some notion of a current state, and then you've got a notion of successor states, right? So each child of this node is some successor. And you keep going, right? So from each child, you've got more successors and so forth. Now, this little search tree I'm drawing is pretty conservative. What do I mean by pretty conservative? This is the search tree that would apply if you were playing a two-player perfect information game where on every turn you have two legal moves. We're going to go with this for a bit because it shows why we wind up engineering these things the way that we do. But I just want you to be conscious of the sheer absurdity of thinking about a game that has two legal moves per turn and where that leads us. Like even tic-tac-toe is somewhat richer than this. Okay. So here's the issue, right? We're being adversarial. That is, when we're thinking about the maze, whatever foibles and issues that might arise, you didn't have an enemy. You didn't have somebody who was out to get you, right? Here you do. Now, what does that imply? With the maze, the search is in a situation where there's every incentive for it to be as short as possible. With a game, it doesn't really apply now, does it? Because, see, I'm considering what is every possible move I can make. Both of them, right? And I imagine what the board looks like given those moves. But then I also have to envision, once I've made those moves, my opponent is going to think about how to respond. So my opponent is going to have a whole bunch of response moves over here. And then I'm going to have to think about how I respond to those responses. And see, at every stage, what we're doing is selecting moves that maximize our chance of winning and minimize our opponent's chance of winning, which are, of course, the same thing, since it's a zero-sum game. But the kicker about this, right, is that in any interesting game, you've got strategies available that effectively prolong the game almost indefinitely, right? You've got to have ways of pushing off your opponent's chances of victory. So the tendency is for the depth of this tree to be extremely difficult to constrain. Like really, really difficult. Like it just keeps going and going. And what are the implications of this? Well, we're going to kind of do a little exercise inspired by the 2048 game, just for laughs, right? So if at the first level I've got 2 options, then at the next level I've got 4, and then the next level I've got 8. At some given level D, I've got 2 to the D power options. And it doesn't take that many levels for this number to get relatively ridiculous. So if, for example, I'm thinking about a depth of 16, now I'm at 65,536 nodes in my fringe. And if I go to a 17th move, it continues to get absurd. So it turns out that in practice, when it comes to this type of game tree searching, this observation has 2 extremely important implications. The first of which is give up. I'm serious about this. But we have to be clear about what we're giving up. What we give up in practice is a search that extends to every possible game-ending condition from the present state. In general, unless we're talking tic-tac-toe, in which case you actually can do this. Actually, what's the maximum depth of a tic-tac-toe game anyway?
Is it 9 or is it 8? Because by the 8th one, you've already made like all the possible decisions, so it's kind of forced.
Right. It's essentially 8, like Eric is saying, right? Because you've got 9 squares. You strictly alternate players. The player making that 8th move has essentially picked the 9th move. Yeah. So that's a depth of 8. You've basically got a relatively small number of options, 8 times 7 times 6 times 5, on each move or whatever. So actually, you can do an exhaustive search for tic-tac-toe. That'll work. But there's a reason tic-tac-toe ceases to be interesting beyond approximately the age of 6. Right. I mean, let's face it. I've had to play a lot of tic-tac-toe with kids in my life. But most of them have outgrown that. Not quite all. Anyway, so we give up. But we're going to give up strategically. Okay? Specifically, when we give up, what we're going to do is we're going to say, there's a certain depth we're going to go to, and then we're going to stop. In other words, we introduce the notion of a depth cutoff, a maximum depth. So especially in early AIs, it was really, really common to say, well, I want to play at level 6 or level 8. And that number often translated directly into the depth cutoff for the tree search algorithm. And so it kind of follows, right? The deeper it goes, the more information it has about the game and the more challenging the opponent's going to be. But we still have to think about what are we going to do when we hit the depth cutoff. And so what we're going to do is we're going to estimate the game outcome. Here's that estimation idea again. So this is a very different kind of estimation than we do in A*. In A*, we're estimating how much further do I have to go. With this adversarial search, we're estimating, well, I've gone as far as I'm going to go. What's the probable outcome given what I know? And so this estimator is called a board evaluation function. A board evaluation function. So it's a function that examines the current state of the game board and turns that into some number that says something about the quality of the position for that player. And in addition to the term board evaluation function, you also see this called, instead of a function, a heuristic. So we can see that the general idea of a heuristic is coming up with a numerical estimate when, for computational reasons, you're restricted on the calculations you can do. So that's one way we give up. That's one way we address this situation. We give up. There's another. And that other way is simply a matter of contemplating the amount of memory that we need to retain these nodes. But it's also a matter of contemplating what do we even need to retain. Here's what I mean. In the case of A*, especially for these maze solving and puzzle solving kinds of things, we need to find our way back, right? We need to be able to trace backwards from where we were back to the start so that we've got a concrete solution we can employ. In the case of a game tree search, we actually don't need to do that. All we really want to do is assess out of all of my current live options, which one should I take? I'll then make that move, and now my opponent is going to do something in response. Do I know what it is? No. It's up to them because they're my enemy. Right? I don't get to pick what they do. If I did, it wouldn't be terribly interesting. So there's no real point in storing a notion of this is my path to victory at the end of the game that I know right now. So that also has an impact on how we conceptualize the search strategy. Specifically, what we tend to do with game tree search is to use a depth first search. We use depth first search. And this winds up having some other advantages that we're going to explore in a few minutes. But the single biggest advantage of using depth first search is that we're only retaining in memory essentially one pathway worth of nodes at any given time. In terms of our depth cutoff, we're only using linear space. So, you trace this out, see where that goes, you backtrack, you consider that guy, you come back here, this is deallocated. This is no longer in RAM, right? Well, once the garbage collector gets a hold of it. Then you do the same thing here. You come down, you consider that, come up here, consider that. You've got a value. This node, these values are compared, it picks one. All of this subtree is now gone from RAM. Right. Comes back up here, and it proceeds thusly. So depth first search winds up having some serious memory advantages when it comes to thinking about this notion of a game tree search. And it's going to have some other advantages too, but that's a big one. So a consequence of this is because we know we're going to do depth first search, the easiest way in general to perform a depth first search is naturally to use recursion. And the reason that we wish to use recursion is that, and in general, the reason to use recursion is that you've got an algorithm that needs a stack to maintain information. What recursion gives you is a free stack because you're using the program call stack to store information. So when we think about this in recursive terms, we start up here, we generate our successors, and then for each successor, we perform a recursive call. So we do the first recursive call, and now the activation record for that function retains the information about all of those nodes that have been generated, right? You don't have to do anything special to store that. You come down here, you do the same thing, you generate the successors, you make a recursive call, you do it again, you come down here, we've hit our depth cutoff. And the beauty of it is, down here at our depth cutoff, you just return, and thanks to recursion, where you paused in your last calculation, all the data is just waiting there for you by the seeming magic of recursion. So recursive implementations tend to be the way that these things are done in practice. And this winds up being a really nice use of recursion. I think we've maybe discussed in prior classes, some uses of recursion are nicer than others. The factorial function is kind of a canonical example of recursion. Turns out recursion is sort of a dumb way to implement that, right? Because you wind up using all of this storage space that you don't need because you could just implement the silly thing with a loop. With this, sure, you can implement this with a loop, but you had better show up with a stack. And so recursion winds up being a really elegant way to formulate it. Any questions so far? Any questions so far before we get into more lower level detail? Okay, so what we're going to start with is a search algorithm that is known as Negamax. So what's the big idea with Negamax? The concept of Negamax is that at each level, you're trying to maximize the value of taking that move. The nega is at each recursive level and you drop down, you negate the rating you get one level below. Why? Because it was from your opponent's point of view. So by negating the maximum you got from one level below, you should get some nice estimates. Let me sketch out an example of what this might look like in a practical sense. So if we come back to this articulate little game tree over here, at the top level, there's going to be the player that's the first mover. In other words, the player whose turn it is, who's trying to reason about what's going to happen. Personally, I like to call that player the protagonist. Okay? So the protagonist has some number of possible moves, in this case 2, because space. And so generates some successor boards. But now, when evaluating the successor boards, it has to be done from the point of view of an adversary. No, don't clear canvas. No, I just want my eraser. There we go. Okay. So we have the adversary at this level. So this level is from the adversary's point of view. And then here it's from the protagonist and then the adversary. So let's just imagine a possible execution of this algorithmic idea. Okay? So the protagonist has generated some successor states. The protagonist wants to know, how good is this board? So we do recursion. And then here, we're looking at it from the adversary's point of view. And we ask, how good is this board? Well, I don't know. Let's keep looking. And we come down here. How good is this board? Oh, I don't know. Let's keep looking. How good is this board? Well, you know what? We have hit our depth cutoff. It is time to take a stand and stop passing the buck. Now, the convention, and this convention is not absolutely necessary to follow. As long as you're internally consistent in your own code, it doesn't really matter. But the convention is to say something like a winning board is a 1 and a losing board is a -1. Again, it's just a convention. If in your own implementation a winning board is 500,000 and a losing board is -500,000, that's fine with me. I don't particularly care because it's still going to work. But I think the 1 and -1 provides a fairly intuitive way of thinking about things. And then, of course, a 0 would be, I expect a draw. So we get down to this node. We've hit our depth cutoff. Let's say that the board evaluation function rates this as a 0.5. This is a 0.5. Okay, well, then up here we're like, well, we still need more information. What about that one? Let's say that one comes in at a 0.25. Now, over here we have to decide which is preferable. Which is the preferable move? But aha, here's the nega. We need to negate both of these values because the values were expressed in terms of my opponent. Right? So I negate them. And so if I negate them, I find that my preferred value is -0.25. Because -0.25 is the maximum of -0.25 and -5. Okay, so that was interesting. We've evaluated this node. Now we come to this node. And so at this node, we have the same kind of a process. And we come down here and we find out, just as life happens, this one is also a 0.5. Okay. And then we look at this next one, and it happens to be a 0.75. I'm not organizing these numbers very well. You're just going to have to forgive me. So these get negated, and so at this node, we get a -0.5. But now, going up a level, we negate again, right? And so we look at 0.25.5. Yeah, there we are. And that's how the process, proceeds. We just swap at every level. Okay? So, actually, I got this backwards. Just a second. No, that's right. Yeah. It's okay. All right. So, what we're going to do then at this point is, having seen conceptually how this works out, let's imagine it as pseudocode. It's kind of a pseudocode algorithm. So this algorithm negamax has to have some notion of a board position, and then some idea of who the current player is. And then typically we also supply this depth cutoff. And so the traditional way to implement this, because it leads to a very simple implementation, is for this depth cutoff to be expressed as a value that on each recursive call we subtract 1 from it. So once my depth is 0, it's time to apply my board evaluation function. Okay. So what's this going to look like? Well, we're going to kick it off with the base case. So if, the depth is 0 or POS is game over, then we're done. Then we're going to return. Actually, I wouldn't necessarily do it like this. I would probably split them up. So actually, I'm going to go ahead and split them up. Sorry about that. We're going to start with if game over. Why? Because boy, is that easy to calculate, right? So if win, return, not a -1. Return a 1. If lose, -1. Draw 0. So otherwise, we're looking at, is the depth 0? Then we're going to call our heuristic on the position, and that's the value we're going to return. Otherwise, it's time to do some recursioning. So what's that going to look like? You're basically going to say something like the following. The max, the best value seen so far, is -1. That is, the best thing you've seen so far is the worst possible outcome, -1. And then you say something like, for each successor, and within this notion of successor, clearly there's some function that generates these successor nodes. What does that look like? Well, your data structure for your board will no doubt have some way of saying, here are all the legal moves. Here are all the legal moves. And so then from there, what you do is you traverse that collection of legal moves that you get back. And for each legal move, you make a copy of the board, you apply it, there you are. You've got a successor. So for each successor, we'll say that max equals the maximum of itself and the recursive call, but negated. Negative negamax with the successor, the other player, and the depth -1. This is going to look something like that. And then when you're done, you return the max. So this is negamax. This is negamax. It's pretty effective at doing what it does. You'll be implementing this, of course. Not a shocker, right? But it turns out there are some fairly clever, hacky things we can do that improve its performance. rather considerably. What do I mean? Actually, hacky isn't even the right word. Like, provably equivalent and less work is more along the lines of what I'm talking about. So what do I mean? Here's what I mean. Remember this guy over here? This 0.75 hanging out? There's no possible way that that was going anywhere. What do I mean by no possible way? Because we're doing depth-first search, when we hit these lower nodes, we've actually got some extra information, namely the outcomes of the search on the earlier branches. Here's what I mean. I came down here and I found this 0.5 and this 0.25. And so negative 0.25 was, as where this was going to hold it. And now, see, when I come over here, I can tell it that this negative 0.25 that I came up with, when it gets inverted going down, is kind of a ceiling on how useful stuff's going to be over here. So see, once this thing came in at a 0.5, because I know I can hold them to a 0.25, I'm done. I didn't even have to look at this node. So it's yeah.
Are those values stored in ascending order? Like, I mean, coming from like the bottom child to the parent, and are they necessarily in ascending order?
So they're actually going to be stored entirely in local variables, which are stored in the stack frames of the recursion. So, which we'll go over in just a second. So this idea of being able to say, well, it can't get any worse than this, or it can't get any better than this, provably leads to a modification to this algorithm known as alpha beta pruning. So the idea of alpha beta pruning is to say we have definite information which proves that there's part of the tree we don't need to explore. So that in turn lets the search run quite a bit faster if there are just lots of nodes you can ignore. The benefits of alpha beta pruning, are not going to be as manifest with this branching factor of 2 that we're looking at. Bear in mind, this is just for demonstration purposes. Opening position of checkers. How many possible moves are there? Anybody? There's a lot of dissension here.
Because the 4 pieces in the middle have 2 choices, and the ones on the edge each have 1.
So
Because you got 6 pieces across there, 4 of them have 2 choices.
maybe we need to visualize this.
Yeah.
Just a second, and we will visualize this.
Okay. There are 4 cities in a row.
Yeah, what happens when you get to that?
Yeah, so here's a checkerboard.
Okay, yeah, there's 4
Yeah.
rows. There's 4 rows. Okay.
Yeah. So how many distinct moves do we have? Let's see. 1, 2, 3, 4,
And
5, 6, 7. Sometimes you really just have to look at it. It was getting too abstract. Yeah, so we've got 7 possible moves, right? And then in response, there's a similar number. And as the board starts to clear, the number goes up and up and up. Now, using your imaginations just a little bit, right? For chess, same grid size, how many distinct opening moves are there? How do you come up with 12, Austin?
Well, there, you got the knights, which can go two different ways. So there's two of them.
So it's
And
four.
then there's eight. Well, it depends on, can
Oh,
pawns
two
also
and
move
two.
up two?
They can move
Yeah.
2 on the first move.
The,
Yeah.
okay, the pawns all have 16 together, and then
So
the
20.
knights would have
20.
Forgot about that.
No problem. Yowza. 20 possible moves, confronted with 20 possible responses, and again, it only goes up, at least until the carnage is over.
Yeah.
And both armies are greatly attenuated in size. Right? Wow. So the point here is if the use of alpha beta pruning lets us cut off, say, at the halfway point as we're expanding successors, we can effectively, seriously increase the additional depth we can explore. So let's examine what this alpha beta pruning idea looks like algorithmically. So alpha beta pruning follows the same essential outline as Negamax. Okay? It's really doing the same stuff. The difference is it's going to, in this for loop, occasionally try to cut things off early. To achieve that, we supply 2 extra parameters. Anyone care to guess the names of the 2 extra parameters as they are held by convention? Yeah. There's alpha and there's beta. They are terrible names because they don't tell you anything about their meaning. But tradition is what it is. Let me explain what they mean. Alpha represents best outcome for our protagonist. Beta represents best outcome for our adversary. This is not altogether fair. Beta really represents the worst outcome for our protagonist. So initially, on our very first call, so alpha and beta are extra parameters here to Negamax. So we go from 3 to 5 parameters, which leads to, of course, an incredibly ugly function, but it'll do for now. So on the initial call, we send in alpha as -1 and beta as 1. Now, what does this mean? What it means is that when we begin the search, the best outcome for the protagonist we know of is to lose. Right? And actually, beta is the worst outcome for the adversary. The worst outcome for the adversary is for the protagonist to win. Sorry, I mixed that up. Okay. But that's what beta is really saying is, let me fix my text here since it's misleading. Okay, that's the worst outcome that my adversary can cause. And so at the start, the best thing I can cause is for myself to lose, and the worst thing my adversary can cause is for me to win. So what we can do is progressively alter these values as information becomes available with the following goal. If at any time alpha is greater than or equal to beta, we can return. Now, why is that the case? If my best outcome that I can guarantee beats the worst outcome for my adversary that he can hold me to, there's just no point in continuing to look. So at this point, I just quit. And there's no particular reason to do that, because as we keep negating things, at some point we're just going to give up. So concretely, how does our pseudocode change? So the first thing is right around here is our if statement. Next, we are going to rename max to be alpha. So one of the interesting things about alpha beta search is alpha was actually sitting there the whole time. It's our max. Okay. But of course, we just got to rename it alpha. And so something closely related to this is that this line goes away, because alpha is going to come in as a parameter. So we need not initialize it as a local variable. And it's really important that it comes in as a parameter. See, we were just putting max at -1 all the time in the past because that was all the information we had. Now we're going to have information about what's happened elsewhere in the search tree. And with that information from elsewhere in the search tree, we actually get to start max higher, because we know we can get at least that good. We don't really have anything more to offer from here without that. The other huge change is in our recursive call. Why is there a huge change there? Because we added 2 parameters, and boy, you'd better believe we need to supply them. So how do we supply these parameters? Here it gets a little bit subtle. You're going to have to bear with me. Okay. For alpha, we are going to supply negative beta. And for beta, we are going to supply negative alpha. We are going to switch them and negate them. Now, why is that? Remember, alpha is the perspective of the protagonist. Beta is the perspective of the adversary. When you go down a level, you switch perspectives. The other thing is, though, when you switch perspectives, you've also got to invert the values, because we're negating the values on every level. And so that's what we do. And so with this in place, we would never even have looked at that node. And so what happens is, in the left part of the search tree, you tend to fill it out pretty thoroughly. But as you move towards the right-hand portion of the search tree, you start looking at less and less of it. And eventually, alpha beta works its magic, and you get to go deeper. I see a question in a second.
If you are never considering those nodes, when were they computed? Like, did you assign them at the beginning?
They were never computed. It's depth first search. So, yeah, Dan.
I think I've got a similar question to what
Yeah.
he's asking. As the algorithm goes through and computes these, I assume like you get to the first level, and it's assuming with just the information it knows at that point, with that board state, what it thinks the chance to win is.
That's right.
And then it goes one level deeper and looks at the new board.
Oh, actually, at that higher level, it doesn't know anything.
So it hasn't calculated value yet.
Right. It doesn't calculate a value until something comes back from a base case.
Okay, so it can't be fooled like, oh, this position looks bad, but it gets better 2 moves down because it didn't evaluate the first position until it came back up.
Both correct and incorrect. Here's what I mean. From the perspective of the interior nodes I put up here, that is absolutely true. It does not, however, preclude the fact that once you hit your depth cutoff and you evaluate it, it actually might be fooled because there's something really good coming down the line. And that's sort of a known hazard. And we're going to talk about some ways of dealing with that. But yeah, interiorly, that has no effect on alpha beta, because it's not It's not going to assign a value to a node until it's completely explored its subtree.
Then kind of keeping that in mind, how can it ever skip anything except for a terminal node? Because, terminal nodes, you could say, well, it looks like since it hasn't evaluated any of the ones further up, how can it ever know to roll those out? Because it hasn't calculated value until it went all the way down and came back up.
So here's the issue. Here are the only two actions is really deceptive, okay? So let's say you've come up here and now there's a concrete value. It comes over here, it passes down its alpha, and that alpha affects this entire subtree. So at some point, it may hit an interior node that can be ruled out completely because of the value of the node here. Because this node is aware of the alpha value obtained from this entire left subtree.
I guess I'm so confused, and I may just have to sit with it and think about it later.
Oh, well, let's talk about it, yeah.
But, okay, I'm going down the right-hand side of the tree.
Yeah,
And so I get to that node where you want to start excluding things.
yeah.
I don't calculate a value for that node until I go all the way down the
Right.
successor.
You won't be able to do anything till you hit this guy.
Okay, so you have to go all the way down the left branch of anything before you can start excluding anything.
Right. Once you get here, now you're up here, and you're getting a beta value back through the recursion, and now you can compare it against this alpha.
So I'm at least
Yeah.
going to have to go down the left side of everything.
You must go all the way down the left of every subtree. Yeah, that's a great question. I'm glad you dug into it like this. Alpha beta pruning does not help you with the left-hand side. You must always fully explore the left. It's the right-hand side where we're trying to whack some weeds. I'm feeling the question.
What if going right might have been a better approach? Like, what's magical about the left side?
Right. What if something on the right would have been a better approach? The key to alpha beta pruning is that when you negate it at the next level, the opponent isn't going to want that better approach. The opponent's going to see, oh, you had a win over there. Forget that move. Right? That's really the key to all of this, is the fact that the estimates are constantly being inverted because the perspective is changing. And that's really the key to its success, is it's actually precisely that. When you see something really great that your opponent is never going to let you do, there's no point in exploring it further. I mean, it's sort of sad, but there it is, right? Other questions so far? So I think what we're going to do is actually kind of do this example again with the alpha beta idea and see where we land. So I'm going to go find some clean real estate. And I'm going to draw out my search tree. Note that this is purely abstract, like we've been discussing. You will never have all of this in memory at the same time, because we're depth first searching and we're just going to be real conservative that way. Now, as we think about this, bearing in mind that all of these local variables are stored on the stack, what we have are alpha and beta values existing in parallel at different levels. So the alpha beta level down here at this level isn't going to be the alpha beta up here. The one down here is going to be heavily influenced by what's up here. And ultimately what's up here will be influenced by what's down here, but they're separate calculations intrinsically. So we're going to think of this in terms of levels. So we've got alpha, beta there, alpha and beta there, alpha and beta there, and alpha and beta there. And we're going to see how these change slowly over time. So the beginning of time, alpha is -1, beta is 1. So now we do a recursion. and we pass down alpha and beta. And what we're going to do is we're going to switch them. So this alpha gets this beta value, but then it negates it. And they wind up looking, in this case, exactly the same. So far, pretty dull. And it's going to continue like that until we get to the depth cutoff. So now we're at the depth cutoff. And we're going to say this node evaluates at 0.5. What that means, whoops, is that alpha over here has gone from -1 to 0.5. So the best that I can do, that I can guarantee, has gone up to a 0.5. So now I'm going to consider this one. So this one is going to be a 0.25. That has no effect on alpha. Okay? But now is where things get a little bit tricky. Actually, things got really tricky because I actually screwed up this explanation. Sorry, just a second. Those go away. Okay. What do I mean? These successors were generated from a particular point of view. They then get arbitrated from the opposite point of view up here. So these guys are going to go up the tree, but they're going to get negated. So, whoops, I'm erasing. So you got I'm still erasing. There we go. I've got -0.5 there, -0.25 there. Now we're assessing this alpha. It's going to say the -0.25 is the maximum of the -0.5, -0.25. So now I genuinely have an alpha update. -0.25. So far, this hasn't really done anything. Now we come to this node. Yeah, Dan.
Just a quick question there. Is that because it looked at the two things at the end and it's deciding the one for my adversary? My adversary is going to make his best choice.
Yep.
The adversary's best choice would be -2.5, so I'm going to assume that's what he did.
Yeah.
Okay.
Yeah, let me go back over that because what Dan just asked about is really, really important. From the point of view of this player, this is the better move. But what we're really concerned about here is the perspective of the opponent. From the opponent's point of view, this is the better move. So the opponent says, okay, that's what I'm going with. In other words, the opponent is picking between these moves. The opponent finds if I make this move, my enemy pulls a 0.5. If I make this move, my enemy pulls a 0.25. If I'm choosing between them, I'm going with this. Everybody with me? So now we're over here. And the alpha is the -0.25. Beta is still 1. We come down here, and now we're switching alpha and beta. So actually, we did have them down here. So alpha is now -1, and beta is 0.25 positive. Here we go. Yeah, so now here's the magic. This one comes in at 0.5. Alpha is now 0.5. Now I get to quit. The reason I get to quit is, imagine this came in at 0.75. Well, at this node, he's going to be like, who cares? I negated you. And when I'm looking at -0.75 versus -0.5, I'm going to go with the -0.5. And life goes on. Yeah, there is literally no benefit to expanding this node. And notice that this same confluence of events can happen regardless as to whether this was produced by a board evaluation function or if it were the interior node of a deeper search. It hits here, it's done, right? So what happens? This sends back a -0.5, Negative 0.5 is not greater than negative 0.25. So at this level, let's see. I got myself a little mixed up here. Yeah, so this one is happily negative 0.25. This was negative point. Dang it. Sorry. Okay, let me erase again. So I got to confess, it's pretty easy to get mixed up doing alpha beta search. So let me just stop for a second and make sure this is making sense. We came up here. The value of this node is negative 0.25. So negative 0.25. We came up here. The value of this node is negative 0.5. Now we reverse them, and it's going to pick, yeah, Dan.
So then when you X'd out, it put a 0.1.
Mm-hmm.
Why wouldn't it have been considered?
So the 0.1 isn't going to maximize at this level. The 0.5 is going to eat it up.
But from the opponent's perspective, a 0.1 would be 0.5, so wouldn't it beat it back up? And then
That happens one level later, right? So at this level, I'm trying to pick them on what's the best I've got here. And then I go up another level. And that's sort of where it works out. Yeah. So that's the basic idea of alpha beta search. Algorithmically, it's actually fairly straightforward. You've got the negamax outline, and then you just kind of inject alpha and beta here at this stage. For your convenience, because I know how bad my handwriting is, I've got a nice, neat, readable version of this linked from the project page for your reference. So there's alpha beta, and then here's a nice outline of negamax for you. Okay. So having said all that, there's another issue I want to go over before I go over your assignment. Okay. And that issue I want to go over is something Dan alluded to earlier, which is the notion of a search horizon. So what do I mean by a search horizon? What I mean is you hit the board evaluation cutoff. And when you hit that, something might look really good, but then it sets you up for some kind of nasty trap, right? It's just that in that position, the evaluation looked good. What do I mean by an evaluation looking good? An example of a board evaluation function you might use might be pure material. So you might say, let me add up the total number of checkers I have and subtract the number of checkers my opponent has. And then somehow scale that into the negative 1-to-1, and that's my evaluation function. So the more of a material advantage I have, the better. Well, it might be the case that you have a move that puts you in a situation of a strong material advantage that then sets you up to get wiped out by your opponent in some way. So there are two types of techniques for going past this horizon that often are used in practice. The first, and these were both developed for chess algorithms. These are long after the time of Arthur Samuel. There's search until quiescent. The idea here is don't cut off if the position resulted from a capture. So don't cut off the search if the position resulted from a capture. So once you're past the depth limit, if it resulted from a capture, you go down one more level. You only look at the positions that are produced by more captures. And you keep going until the captures stop. So the idea of search until quiescent is the idea that a board state is quiescent if it didn't result from a capture. They're done killing each other, which of course is really common in something like checkers. So The motivation here is to say, well, in this position, I had a huge material advantage, but it turned out I set myself up to have my opponent triple jump me, and now I'm toast. And so search until quiescent is a way of saying, let's keep going until we get to the end of the triple jumps and stuff. And then let's actually do our evaluation. Related to it, but distinct, is called singular extension. The idea of singular extension is to say if one successor is a lot better than others, keep going. So what's the idea behind singular extension? It's motivated by similar circumstances. One position out of all of the possibilities is somehow much higher rated than the others. Singular extension is about saying, if this happens, let's be paranoid. If something looks really good, it may be hiding something really bad. So singular is really important here. It's only going to continue operating as long as there's one successor that exceeds the quality of the others by some large constant, like a 0.5 or something like that. And it can just be one. If there are more than one that are bigger, like you've got a bunch of good ones and a bunch of bad ones, singular extension does not apply. It's just about saying, this one looked too good to be true. Let's investigate further and find out if it's as good as it's advertised. So that's another modification to this alpha beta search that can have a big impact on performance. So all of this said, let's look over your assignment. So you're going to develop an AI for checkers. I've provided checkers. So here's checkers. Here's how it's laid out for you. The program called Checkers is a checkers game. And you can play it as you like, and you play it by grabbing a piece with the mouse and dragging it. And then you do that for your opponent. And then if you try to do something illegal, like that, it'll say illegal move. Those of you who aren't checkers aficionados, I want you to be aware that in checkers, captures are mandatory. So if it's possible to capture, you must capture. And so likewise, black can't move over here. Black must capture. Checkers has a big subtlety when it comes to negamax, because the most straightforward way to implement it is that if you're eligible for a double jump, the turn just doesn't change. And because captures are mandatory, if you're eligible for a double jump, you must take it. So you'll need to be careful in your negamax implementation to ask the checkerboard class whose turn it is, because it'll keep track for you of whose turn it's going to be. So you can do all this stuff and move by hand. You can also ask the computer to move. And then it'll just move automatically. Now, there are two things that control what it does. You pick an evaluation function from this drop-down menu. And so this works similarly to how it did on the last assignment. And you can pick a search algorithm from this drop-down menu. And so right now, my board evaluation function is that it returns the same number for all board configurations. It has no preference. And the search algorithm is it looks one move ahead and then picks randomly. Yeah. So yeah, now you can just randomly move it out. So part of the fun of this, of course, is that so there a king emerged. Yeah. So the kings have like little double circles. And so forth. So part of the fun of this, right, is this provides a really neat way to play against your opponent, your AI, and see how it does on a move-to-move basis. Now, a lot of what we're going to be doing is playing the AIs against each other. And for that, there's this program, Auto Checkers. So Auto Checkers pops up a fun little interface where you tell it, for player one, what's its eval function, what's its search algorithm, what's its depth limit. You also importantly say, what's the maximum number of moves in a game? Because some of these AIs are just going to be like, my king's hiding in this corner, my king's hiding in this corner. Never the twain shall meet. So you do have to specify a maximum number of games. And then you tell it how many games to run, and it'll run a little tournament. And then it'll tell you the relative outcomes. And it'll also tell you, search nodes expanded and stuff, which for this is a really tiny number because it does no search. So you've got that resource. Let me kind of give you a map of the source code. So searcher is set up as an abstract class. That is, it's like an interface, but it includes a little code with it for you to use. And when you implement your own search algorithm, this one-ply shuffle kind of shows a code skeleton of how to do that. So you're going to want to have some int variable where you track how many nodes you expand, and then you'll return that number through this method. Like those 2 bits you can pretty much just copy, right? But then the biggie is select move. Select move returns a move score object. What's a move score? It's a move and a score. Interiorly, all you care about is the score. How valuable is the position? But at the top level, you really care about the move. What was the move that gave me the best score? And so this is an example of a very bad search algorithm. It calls the checkerboard method getNextBoards to create an array list of checkerboards. It then sets the number of nodes to be the size, because that's all it's going to do. Then it picks a random number to find out which one it's returning. And then in a fit of honesty, it calls the board evaluation function on the one that it returned, just so that you've got a score with it. So this is pretty dumb, but it's a really great benchmark, right? Like, let's say you work really hard on your search algorithm and you're like, I'm ready to test this. First thing you do, you test it against this. If it's worse than random, you've got a bug. Yeah.
So that board, getNextBoards, gets all possible legal moves for us?
Yeah.
That's okay.
Yeah, that's really, really important. Yeah. Oh, I should mention in the auto checkers, if you've got 2 non-random players playing against each other, obviously there are like only 2 possible games, right? So how does it play lots of games against them? It actually plays out a few moves randomly and then uses that as a starting point. So in effect, they're each starting at a random early game position to play against each other. Because otherwise, it would like just always be the same. So that's what that does. So then for evaluators, this evaluator is called no preference, and it returns 0. So this is, again, very much like the heuristics from last time. You've got this one method, evaluate, to implement, and then you get a checkerboard, and what you need to do is examine the board and come up with an evaluation. There are lots of ways you can do this, and I want you all to have fun with this and be creative with it. If necessary, pull out a checkerboard and start challenging each other, or whip up the program and start challenging each other and just sort of see what you think of. Let me go over that. So that's kind of a brief tour of the source code. So the main stuff you're going to be doing is really all you're going to be doing is creating classes that go in the evaluator and the searcher directories. And they're going to be patterned off these 2 examples, but they'll have, unlike these examples, actual algorithmic content. actual content. So let's go over the assignment. So that's set up. I kind of give a tour of the source code there. So the first thing I want you to do is implement a basic material board evaluation function. It should subtract the number of pieces the opponent has from the number of pieces the current player has and return that difference. So simple, enough to get started, not obviously bad. Can be better, but not obviously bad. Next, I want you to implement Negamax, and I want you to figure out what depth can it generally reach in about 10 seconds. So play a game or two against it, pull out a stopwatch, try it on a couple of depth levels and see how long it takes. This number will vary considerably based on the specifics of the board positions. So for this purpose, figure out what the worst case is like. So typically, you're going to have to be a few moves in until you get to the worst case for this. Okay? Then I want you to play against this combination of Negamax and this kind of dumb evaluator. Assess its performance subjectively. In other words, play against it and write down whether you thought it was easy or hard. But what I want you to do in your qualitative assessment is use concrete examples of its play. So be ready to talk about, it was in this position and it did this dumb thing. Or it was in this position and it killed me by doing this. Talk about that kind of thing. Then use auto checkers with your to run your Negamax with that evaluator against a random player 32 times. See how it did quantitatively. How much better is it than random? Then I want you to copy your Negamax, modify it, do alpha beta search. Again, determine the depth it can go in about 10 seconds of time. Talk about the difference that alpha beta search made. Then I want you to play against the alpha beta searcher with the simple evaluator, but the bigger search depth that alpha beta nets. Again, assess its performance. Especially just start feeling like, does it feel smart? Yeah. Once you've done all of this, now you're ready to improve your evaluation function. So at this point, I want you to just come up with some ways to improve it. Maybe you do something with kings. Maybe you do something with mobility. Maybe you have like good squares and bad squares, or good squares and better squares, you know, whatever you'd like. Just come up with something, try to improve it, and now compare the two of them. Much like the last assignment, I'm looking for you to be creative and come up with stuff. I'm not necessarily requiring that what you come up with actually be better. Obviously, you're going for that, but you're not going to get any points off if it turns out it's worse. I'm just assessing, you know, you came up with an idea, there was a basis for it, you assessed it. That's what you're getting graded on. Having done that, I finally want you to improve your search algorithm. I'm requiring you to do 2 modifications, but you can do more if you'd like. I'm not going to stop you if you're feeling ambitious. Okay. So what are some possibilities? You can try out search until quiescent. You can try singular extension. You can create an opening database or a solved endgame database. A transposition table. This is something where it tries to see, I've seen this position before, so I'm not going to keep the search going. In other words, you set up a simple move cache using a hash table, hashing the checkerboard. Implement an ordering heuristic. So something that people sometimes try is to apply the board evaluation function to all the successors and approach them in the order of their evaluation scores in order to force an early alpha beta cutoff. Some say it's great. Others say it's not great. You're welcome to try it out. Or do anything else you want. If it's not, if it's going to be one of the 2 modifications you're doing as part of completing the assignment and it's not on this list, I want you to communicate with me first. You can just shoot me an email or whatever. I just want to make sure that it's something that's reasonable within the scope of the assignment. If you've already done 2 of these and you want to try other stuff, there is no need to communicate with me. Try it out. I look forward to hearing about how it goes. And then you can just keep playing with this until you like how it does. And then in your paper, you're going to summarize all this stuff. Your search strategies, how you modify the board evaluation function, your qualitative assessment, playing against it, then your quantitative assessments as well. So on Tuesday, I'm going to have each of you share with the class, and I think we'll just do it from your seats, kind of like we did last time. So I want you to talk about how far you've gotten, what kind of performance you got from your alpha beta, what kinds of things you're trying with your evaluation function. So kind of give a midway progress report. And then Thursday, we're going to have each of you go over final results. I'll come up with a pairings again to do the presentations together, which I thought helped with our time efficiency considerably. And if there's some time left over, maybe we'll whip out some of the programs and just play them for the rest of the class. So in terms of time management and the like, what I would recommend is you really, really want to get this basic material evaluation and the basic Negamax working in the next day or so. These are like the concrete foundation of getting anywhere on this assignment. So you want to nail these, you want to get them down. They're not too difficult. Just knock those out. You want to knock them out early, partly because you want to give yourself some think time to ponder what creative things you're going to do with the evaluation functions. So knock those out early on. I mean, this one, this should be 5 to 10 minutes, right? This is, look at the checkerboard class, find out how many pieces there are of my color, you know. So some code reading, but then bam, you should be able to knock that out. Negamax, probably a little bit longer, but like you saw, the algorithm itself is really pretty straightforward. And then from there, now you've got some, so if you basically by the weekend, you've got those in place. Now you've got some space to work on the other creative aspects of it and to do the more advanced stuff. We'll have a check-in on Tuesday, and then it'll be due on Thursday. Any questions? Happy checkering. See you Tuesday.